Welcome everyone to the next talk on our Paleobiodiversity and Evolution Symposium. Our next speaker is Dr. Andrea Sanchez Meseguer from the Real Jardín Botánico de Madrid in Spain. Unfortunately, Dr. Andrea was not able to be here with us right now, so she kindly sent us a video of her presentation. So I believe she will not be able to answer questions unless she is able to connect with us afterwards. So we'll play the video that she kindly recorded, and questions can be sent to her email afterwards, after the talk. So thank you very much, Andrea, for sending us the video, for accepting giving your talk here with us. And that's it. Thank you very much.
Hello, my name is Andrea Sanchez Meseguer. I work in the Royal Botanical Garden of Madrid, and I'm going to talk today about the origin of the latitudinal biodiversity pattern gradient. Sorry. I think most of you know this pattern. It describes the increase of species richness that occurs from the pole toward the equator, as represented in this graphic on the right, with the number of species plotted as a function of the latitude. Okay, so when you think there is nothing else to say about this pattern, I'm going to try to convince you that there are still many investigations that need to be done on it. So there have been many hypotheses to explain the origin of this pattern. Here I present some of the most popular ones. For example, the tropical niche conservatives of Vince and Donahue. This hypothesis posits that most diversity originated in the equator under tropical conditions, and therefore they have more difficulties to enter into the temperate zone, meaning that time and limited dispersal have been used to explain the origin of this latitudinal diversity gradient. The out of the tropics model of Jablonski posits that in addition to limited dispersal, diversification rates might be higher under tropical conditions in the equator, where speciation is higher and extinction is lower. Other more recent hypotheses suggest the speciation rate might actually be higher in the Holarctic regions, in the northern latitudes, but extinction is also higher in these latitudes, and so turnover is elevated. So it's elevated speciation and elevated extinction. So as you might see, all these hypotheses differ in that they propose different mechanisms, different processes that could have shaped this pattern. But these hypotheses, they have in common that most of them assume that the origin of diversity occurred in the equator, and diversity accumulated at lower rates in other regions in the higher latitudes. So they assume that the steep shape of the latitudinal diversity gradient that we observe today might have been persistent through time. However, there are new fossil investigations that suggest that the shape of the LDG, the latitudinal diversity gradient, might have not been persistent through time. And there are some groups for which there could have been comparable diversity levels across latitudes, as we represent here with this flatter pattern. This has been shown for dinosaurs, birds, mammals, turtles. Well, these are just examples. There are a review of evidence in this paper of Manu, but all this evidence suggests that the diversity levels in the northern hemisphere could have been comparable to diversity levels in the equator in some periods of the past. In fact, these fossil investigations, they further suggest that the steep shape of the latitudinal diversity gradient that we observe today might have been restricted to the relative few coal house intervals on Earth history, like the Ordovician, the Carboniferous, or the Neogen. Whether most of the phanerozoic might have been characterized by greenhouse climates and a flatter pattern. Okay, so we consider that this line of evidence, this new line of evidence, might suggest that rather than explaining why diversity accumulated slowly through time in the northern hemisphere due to limited dispersal, equatorial diversification, or high turnover in the Holarctic, We rather need to explain how diversity has been lost through time in the higher latitudes to conform the current shape of the LDG, of the latitudinal diversity gradient. And well, you might think that hypotheses of extinction have been proposed for decades, which is true, but the problem is that up to date, it has been difficult to prove diversity loss. There have been a lot of evidence in favor of high turnover, but turnover in the Arctic can just explain the slow accumulation of lineage through time, but cannot explain diversity loss. For diversity loss, you need extinction to be higher than speciation. Okay, so in our study, we wanted to confront these two groups of hypotheses, the lower diversity accumulation versus the higher diversity loss scenarios. Under the lower diversity accumulation, we might expect that extinction in the Arctic might be lower than speciation or comparable, and that dispersals out of the equator prevail over into the equator dispersals. Whether under higher Arctic diversity loss scenarios, we might expect that that extinction is superior than speciation in the Arctic, and the dispersals into the equator prevail. Well, so we have tested this hypothesis using phylogenetic data for testudines, lepidosaurs, including lizards, snakes, and worm lizards, and crocodiles. And we also use fossil data that we download and curated from the Paleobiology database. So the first thing that we did is that we divided the fossil database into fossils from the equator and fossils from the Arctic. And we studied diversification dynamics, meaning origination, extinction, and preservation rates through time for these independent databases in 3 different periods. I'm going to show it here. Well, we use it, the Bayesian pirate model of Silvestro. And we consider 3 periods, and as I was saying, the greenhouse period of the Triassic, Jurassic, and Cretacic, the Paleogene transition to cold, and the Neogene cool period, sorry. So our results are present here. Below, I just plot the number of fossils in each data set, Arctic versus equatorial in each of the groups. So the first thing we can see is that diversification dynamics seems to be comparable, diversification rates seem to be comparable between equatorial and Arctic region during the greenhouse period of the Cretaceous for all the groups, as you can see here, for turtles, for crocodiles, and for squamates. These equal diversification rates might be in agreement with this idea of the existence of a flattened pattern during this period. Next, we observed that during the transition to cold and seasonal climates in the Arctic, we observed that diversity rates decrease in the Arctic for turtles and crocodiles, and diversification rates go below 0. So that means extinction is superior than speciation, and diversity loss occur in this region for this taxa. So this is in agreement with the idea of diversity loss in the higher latitudes. For squamates, we observe also a decrease in diversification rates in both areas, but it's the equatorial data space that lost diversity following this analysis. Well, we think we have to be careful with interpretation of the equatorial database because, as you can see, confidence intervals are huge for this database, probably because the low number of fossil records. So the next things we did was to study biographic, to reconstruct biographic areas for these groups using the dispersal extinction cladogenetic model of Ryan Smith, the DEC model. This slide shows an example of how these analyses were run for tortoise. I'll show you in the next slides information for the other groups. What we did is to compare an unconstrained model, so a regular model in which ancestral states are reconstructed based on the distribution of present species and their phylogenetic relationships. We compare this model with what we call a fossil constrained model, so a model in which fossils were assigned to phylogenetic nodes, And the distribution of these fossils were used to constrain the biographic reconstruction, okay? So the results of this analysis are shown here. In both cases, the pie charts represent the most likely ancestral reconstruction. The arrows represent the dispersal events, infer dispersal events, and the red crosses represent a range extinction. So this is not pure lineage extinction, but mostly represent when a lineage is extirpated from part of its ancestral area, okay? So at first look, you might see that the results are quite different. Based on the unconstrained model, we reconstructed that the ancestor of turtle was distributed in the equator from where it dispersed to the rest of the world. In contrast, when we consider fossil information, the ancestor of turtles was widespread. And what we see is that there has been a repeated loss of the Holarctic distribution through the evolution of this group, as indicated by the red crosses. So these plots represent the same information, but for all the groups. In this case, what we have done is that we have extracted just the dispersal events, and we differentiate dispersal events into the equator from the dispersal events out of the equator, okay? So here I've just plotted the results of the unconstrained model, so no fossils so far with the dotted lines. And what you can see, for example, in test studies, in turtles, is that the dispersals out of the equator prevail over dispersals into the equator during most of the history of this group. So in agreement with the out of the equator hypothesis. For squamates, we have equivalent levels of dispersal, and no dispersal event is estimated for crocodiles. Well, I'm gonna plot over these curves now the results of the fossil model. They are here. Solid lines represent the fossil model, and dotted lines the unconstrained model. And as you might see, the results change a lot when we consider fossils. The dispersals into the equator largely prevail over dispersals out of the equator in all the groups. So suggesting the opposite scenario, into the equator dispersal for these groups. These plots now reflect range extinctions. So remember, it's the extirpation of the lineage from part of its ancestral range. So again, those are the results without fossils. As you can see, when no fossils are considered, we estimate very low levels of range extinctions in the Arctic for turtles, equivalent levels for squamates, and no any event of range extinction for crocodiles. So now I'm going to plot the results considering fossils, and I think again the scenario changed quite a lot. And when fossils are considered, you see that Holarctic range extinctions prevail in all cases. And this result suggests that range extinction could have occurred in the Holarctic to confirm the shape of the LDG today. So while our biographic and our diversification results together suggest that Holarctic lineage extinctions, range extirpations in the Holarctic as well, and into the equator dispersal could have contributed to depauperate the Holarctic and to confirm the current shape of the latitudinal diversity gradient that we observe today, at least in the case for turtles and crocodiles. For squamates, the evidence is mixed because we found support for range extinction and equator wall dispersals, but no evidence for Holarctic lineage extinctions. So it could be that for this group, a true flattern diversity pattern never existed in the past, or that the fossil record is so incomplete that we cannot have good derivates from it. In all cases, we think that one possibility to explain this transition from a flat to steep diversity gradient in the present could be due to the contraction of the tropical biome that occurred through the Cenozoic. And well, if the elevate temperatures that occurred at the beginning of the Cenozoic, this is the temperature curve, sorry. So if the elevate temperatures that occurred at the beginning of the Cenozoic allowed the expansion of taxa adapted to tropical conditions into the northern latitudes, it's possible that many of these lineages, when extinct or lost part of their distribution, when the tropical biome contracted towards the south. So to summarize, we think the latitudinal diversity gradient is a time variable diversity pattern that have changed through time from a flatter to a steep diversity gradient, possibly in agreement with the major climatic oscillations that have occurred during the Earth history. We propose that the processes that shape this pattern might have also changed through time. We propose that extinction into the equator dispersal might have mediated in the formation of a flatten to a steep gradient, sorry, in this transition. And we hypothesize that maybe diversification in the higher latitudes and out of the equator dispersal could have mediated the previous transition from a steep to a flattened gradient. I say we hypothesize because the truth is that the age of our fossils post-date the last ice house to greenhouse transition before the Triassic. So we cannot test this hypothesis, but at least we found support for equivalent diversification rates between regions during the Cretaceous in agreement with the existence of a flattened pattern in the past. So, well, we just to conclude, I think that we could not have identified these patterns if we would have not included fossils in our analysis, because these kind of patterns that are shaped by extinction might be difficult to recover just based on present evidence only. So this is all. Thanks a lot. I'm very sorry I'm not gonna be in streaming, but I will be happy to answer all the questions that could be put in a chat. I think there's a chat that's gonna be it's gonna be organized. So I'll be happy to respond to the questions and also via email. So thanks a lot.
What a great talk by Andrea. Thank you very much, Andrea, for sending your video. Unfortunately, as I said, she was not able to be here with us today. So please send your questions for Andrea via Discord, or you can also contact her by email. If you do by Discord, we will make sure those questions reach Andrea and she managed to answer those. Okay, thank you very much.